Welcome back to the deep dive. Today we're jumping into this really invisible world. It's one where the most basic particles, the fundamental bits of everything, they just act really weirdly.
Hmm.
Our mission, and we're drawing on some great notes, like those from Andrea Mini, is to figure out quark confinement. Basically, why these tiny things are, well, never found flying solo.
Yeah, and it's more than just some subatomic oddity, this quark confinement thing. It's described by quantum chromodynamics QCD, we usually call it, and it's really fundamental.
Fundamental how?
Well, it directly affects the stability of pretty much everything. It's literally what holds matter, together.
Okay, quark confinement. It sounds a bit dramatic, like they're locked up. What does that practically mean for these particles?
It means quarks are essentially locked inside bigger particles. We call them hadrons. Protons and neutrons are the famous ones. They just
Right.
can't exist by themselves. And the weirdest part, the force holding them, it actually gets stronger the further apart they get.
Whoa, hang on. Stronger, not weaker, like gravity or magnets.
Exactly. That's what's so counterintuitive. It's governed by the strong interaction or the strong nuclear force.
And that involves gluons, right? I've heard that term.
Next slice. The strong interaction is carried or mediated by these particles called gluons. And what's really unique here is that gluons themselves have this property called color charge.
Color charge, not like actual colors.
Okay, no, not red or blue. You can see it's a quantum property, kind of analogous to electric charge. It dictates how quarks and gluons interact. And because gluons have it too, it makes the theory QCD nonlinear, very complex.
Right.
And this force, this strong force, is just incredibly powerful. It's what keeps protons and neutrons packed together in an atom's nucleus, overcoming their natural tendency to fly apart.
Yeah.
That's stability right there.
So gluons hold quarks and hadrons, and they also hold protons and neutrons together. But the way this force acts, you said it changes with distance. That sounds paradoxical.
It really is quite astonishing. When quarks are super close together, like at really high energies, they barely interact. They act almost freely. Yeah, we call it asymptotic freedom. But try to pull them apart even a little bit, that force starts increasing linearly, actually.
Linearly, like
I-
stretching something.
Exactly like stretching an elastic band. The potential energy just builds up the further you stretch it. VR is roughly sigma times R if you want the maths bit.
So, okay, the harder you pull, the harder it pulls back.
Yeah.
You're never going to just snap that band and get a free quark. That just messes with your intuition, doesn't it?
It completely does.
So what happens if you keep pouring energy in, trying to separate two quarks? What's the breaking point?
Well, that's the thing. You keep pulling, the energy in that color field between them just grows and grows until it hits a kind of critical point. But instead of the quark breaking free,
Then?
that stored energy actually transforms into mass. Good old EMC2.
Energy becomes mass.
Whoa. So out of that energy, new particles are created. Specifically, new quark-antiquark pairs pop right out of the vacuum.
Seriously. So you don't get a free quark, you just get more quarks.
You get more hadrons. Those new quarks immediately bind together to form more composite particles. You try to pull one quark out, you end up making a whole bunch of new bound states.
Which is why we've never seen just one quark on its own.
Yeah.
Ever.
Precisely. It's never been observed.
So why? Why this absolute insistence on being paired up or in a group? What's the underlying rule?
It boils down to something called color neutrality. Think back to that color charge.
Okay, the red, green, blue thing you mentioned?
Kind of. Baryons, like protons, they have three quarks, one red, one green, one blue. Together, they're white or color neutral. It balances out.
In mesons.
Mesons are simpler, just one quark and one antiquark. The antiquark has an anti-color, like anti-red. So red and anti-red also make a neutral combination.
So a single quark by itself isn't color neutral.
Exactly. It's got an unbalanced color charge, which is apparently forbidden in nature over long distances, so it instantly tries to bind with others to achieve that neutral state.
And we see the aftermath of this in experiments.
We do. Indirectly, though. At places like CERN, when particles collide at huge energies, we don't see free quarks flying out. We see these sprays, these jets of new particles.
Those are the new hadrons being formed.
That's the interpretation, yes. The quark tries to escape, creates new pairs, and they all hadronize, form hadrons very quickly.
It's amazing we understand this process. We see the evidence. It's fundamental. But there's still a catch, isn't there? Something missing.
There is, yeah. If you look at the big picture, we're very confident about confinement based on experiments and simulations, but a complete, absolutely rigorous mathematical proof that QCD must confine quarks. That's still missing.
No kidding. For something so big.
Yep. It's actually one of the Clay Mathematics Institute's Millennium Prize problems. Solve it, prove confinement directly from the equations of QCD, and there's a $1 million prize waiting.
Wow. That really puts it in perspective.
It shows there are still some really deep questions about the fundamental rules, the basic forces that literally construct our reality.
What a fascinating trip. This elastic band force, energy turning into matter. Quarks really are the ultimate social particles. They just refuse to be alone.
It really makes you wonder, doesn't it? If the very stuff we're made of follows these unbreakable rules of connection, what other hidden rules about reality are still out there, waiting for us to discover? Or maybe prove?
Definitely something to ponder. Keep exploring.